Today we're going to be talking about least squares regression and a case for transformation. So we're going to have a least squares regression that actually doesn't work, and we're going to see what we can do to make it work. Here we have a set of data. My x data is 0 through 4. I'm going to create not a random list, but I'm going to create a set of data using a formula and see if you can determine what that formula is as I create these values. Now clearly I'm squaring my x values to get my y values. And this is going to create a linear regression. This is going to create a power curve, part of a parabola. This is going to be a curved graph. Let's take a look and see what happens. Our least squares regression, based on our TI calculator, we see that we have a y-intercept of -2, a slope of 4, and most importantly here, we have a correlation coefficient that seems to be very strong, 0.959. Basing a decision of linearity solely on the strong correlation coefficient would be a mistake. We would assume we have a strong linear relationship, but take a look at the graph. The data shows a strong curved relationship. This is why we always want to look at the graph before we begin a process. Here we see the regression's equation. I'm going to label it as y hat as a function of x, because what I want to do is I want to take these x values and I want to place them in the equation and find the predicted. What does the line predict? So these values that I'm going to find are going to be the values that fall on the line for any given x value. I'll start with y sub 0, and plugging this in, you'll see that the 4, that term goes away because I'm multiplying by 0, and I end up with -2. Let's go ahead and move on then. I'll take the next x value of 1, and I'm going to plug this into my equation. Plugging in 1 gets me a value here of -2 plus 4. This gives me a value of +2. So that goes into the data table. If I continue on as if I were doing all of these calculations, I can find all of my predicted values via the same process. So let's take a look again. Here's a line. Let's just call this a portion of a line. This is a data point. We'll call it y3. It's the third data point in the set. Directly above it, for the same x value, is my y predicted. I'm going to call this y hat 3. It's the value of y that is predicted from the equation of the line. Here, then, we can formulate the equation of a residual. A residual is found by taking the y value minus the y hat. We can come into our data table then, and we can create our residual column, y minus y hat. So I'm just going to work my way down here, taking the y value minus the y hat value, and these turn out to be my residual values. So this is manually how we would go about calculating the residual. Let's pull out our TI calculators and go through the process using the calculator. Alright, so here's my L1 and my L2. This is the data that I started with. I'm going to highlight my L3 using the spreadsheet feature. I'm going to type in the equation of the line that we got from the least squares regression, -2 plus 4x. But in place of x, I'm going to place my L1 because that's where my x data is. When I go to hit enter here, it will populate my L3 column with my predicted values. These are the y hats. L4, then, that's where I'm going to place my residuals. My residuals will be placed in L4 by highlighting L4, taking my y minus my y hat, which is L2 minus L3, and here you see my residuals. These are the residuals that I will want to plot. Well, let's go ahead and plot them. Get into StatPlot1, make sure it's turned on. It should be. We just did a regression. I want to make sure that I'm looking at the dot-to-dot plot, not connect the dots. L1 and L2, I'm going to need to fix that. My X list, I'm happy with. X is fine. It's going to be my L2 that I'm going to work on here. I want to plot versus my residuals. My residuals need to be on the y-axis. So I'll put in my L4. From the L4, I'm going to jump back to my home screen. I'm going to do a zoom 9 and take a look at my residual plot. Now look at the display. Clearly we have a pattern here. This tells us something we knew already. This is not a linear relationship. Now remember, this is an academic exercise, but this method, this technique, will be used when we go to do real data collection and trying to linearize or transform the data. So let's just step back and think about what we've done. We've taken a set of data that was very clearly nonlinear, and we've manipulated the data. We've done something to one of the x or y variables to create the appearance of linearity. In this case, we transformed the x data, and the way we transformed that was by squaring each of the x values. So if we take each value and we square it based on what we had originally, this power curve, we find that, well, in this case, the data values come up to be exactly what the y values were. But really what we were interested in trying to do was graphing y versus x squared and seeing that all of these data points now fall in a much more linear pattern. Therefore, a straight line relationship is expected.